Welcome back, everybody. Today, it's my great pleasure to introduce our speaker, Jonathan Jaquette. Jonathan is a postdoc at Boston University. He's previously held positions at MSRI and Brandeis. He received his PhD in 2018 from Rutgers University, where he worked under the supervision of Konstantin Mischaikow. Jonathan's an expert in delay differential equations, PDEs, really computer-assisted proof for infinite dimensional problems. We're really happy Jonathan accepted our invitation today to come and talk about his PhD thesis. As many of you will notice, Jonathan's the first person to speak in the seminar twice. And I think when you look at PhD theses in the area of computer-assisted proofs, you know, there are many spectacular dissertations out there, but two that really stand out to me are, of course, the dissertation of Warwick Tucker, where he settled Smale's 14th problem, and also Jonathan's PhD dissertation, where he finally put to rest both Wright's and Jones' conjecture about Wright's equation. So we really appreciated Jonathan accepting our invitation to come and talk about his PhD and have this recorded today for us. And with that said, I'm going to hand things over to Jonathan. We'll hear about his work.
Thank you very much for the kind introduction. I'm going to share my screen. There we go. All right, so as Jay said, I'm going to be speaking about computer-assisted proofs of Wright's and Jones' conjectures with the subtitle of Counting and Discounting Slowly Oscillating Periodic Solutions to a Delayed Differential Equation. So the equation of interest is Wright's equation, which is related to the density of prime numbers. And his first work on Wright's first work on the equation appeared in 1955. But then 10 years later, there was an article published in the Mathematical Gazette, sort of re-deriving the relevance to prime numbers. And it had a foreword by Wright saying that he first ascribed his interest in the equation to Lord Churl's finding an equivalent equation in attempts to prove a heuristic prime number theorem. Several people have asked me how he came across this equation, and I could not answer them since I had long ago forgotten his argument and had destroyed his letter. So, sort of similarly, my interest in Wright's equation doesn't really have much to do with prime numbers. I mean, here you can see there's some oscillations and things seem to decay. There's some oscillations, but mostly there's a decay in the density. But my interest in Wright's equation is just more intrinsic. So what is Wright's equation? It's a delayed differential equation. Here, it's sort of like, it's a delayed logistic equation with a constant delay. It's used to model prime numbers, also oscillations in single species populations. Here, the derivative depends on the delayed time and the current time. And since there's a delay in it, it is a delay differential equation, which means that the natural phase spaces really functions on the unit interval because we have a unit delay. And it's really an infinite dimensional dynamical system. And so there's many ways you can represent solutions. Here, I like to think of this little window here, because here we're seeing the evolution of this initial condition here with alpha is about 1. And you see that things sort of decay, and that if you have two slightly different initial conditions, they'll stay close to each other, but things decay to 0. And so if you plug in a bunch of different initial conditions to get an idea of what's happening in Wright's equation, well, if you have alpha is about 1, well, things decay. And if alpha is 2, then the same initial conditions seem to converge to this periodic solution. And moreover, so between 1 and 2, there's a number called pi over 2, where there's a Hopf bifurcation. And so if you're looking at the linearization of the equation, well, when you linearize, you just have the delayed term. If you assume eigenfunctions are the form e to the lambda t, then eigenvalues have to satisfy this equation. 0 equals lambda plus alpha e to the minus lambda. And so you solve this equation. You can see that it has an infinite number of eigenvalues. This is not going to be a sectorial operator because eigenvalues really shoot up to plus imaginary infinity really quickly. I mean, things are going off. You have a lot of eigenvalues with negative real part. But all that aside, at pi over 2, we have a Hopf bifurcation, and also at pi over 2 plus 2 pi n. And so really the fundamental actors in Wright's equation are the periodic orbits. And the principal actor is the slowly oscillating periodic solutions. And that here is something which is a periodic solution. It's positive for 1 unit of time and negative for 1 unit of time. Why 1? Well, because we have a delay of 1. And so in Wright's original work in 1955, he proved that 0 was a global attractor up to a certain point, and suggested that it would be the global attractor all the way up to pi over 2. In 1962, Jones, G.S. Jones, he wrote a pair of papers where he showed that there's always going to be at least one slowly oscillating periodic solution. And he also did a bunch of numerics, and all the numerics sort of indicated that there was a unique slowly oscillating periodic solution. And so that was his conjecture, that above pi over 2, there's a unique slowly oscillating periodic solution. So, I mean, essentially, this is the sort of bifurcation diagram that we would be expecting here. That over here at pi over 2, so this is a strange sort of horizontal axis. So, but here we're centering at pi over 2 because this is where our bifurcation is, our Hopf bifurcation. And we know that we would expect that there's a Hopf bifurcation, branch of periodic solution grows, their amplitude looks like a square root function, and then it sort of increases. But there's a lot of things that could go wrong, really. And so starting from 1962, well, I guess in Wright, he showed that below 1.5, that there are no slowly oscillating periodic solutions. So I think 0 is the global attractor. And in 1962, Jones showed that, well, there's always going to be at least one slowly oscillating periodic solution over here. And so sort of whittling away to try and get us to prove that we really have this sort of ideal bifurcation diagram that we have in mind. In 1975, Roger Nussbaum showed that the branch that bifurcates from the Hopf bifurcation is a global branch. It goes off to infinity. In 1977, Chow and Mallet-Perret, they showed that there's really not just there's eigenvalues that are crossing, but really all the things that you need for a Hopf bifurcation are satisfied. And in 1989, Benjamin Regala showed that the only types of bifurcations that you could have are essentially fold bifurcations and originating from a Hopf. So there's not going to be any pitchforks or anything. Then, let's see, in 1991, using analytical estimates, it's really paper and pencil. She, a student of Nussbaum, showed that above 5.67, that there's always going to be a unique slowly oscillating periodic solution. And so we have no bifurcations here, no folds, and there's no isolates. In 2010, Jean-Philippe showed that there are no, Jean-Philippe Lessard showed that there's no fold bifurcations and did a rigorous computer-assisted proof from about 10 to the minus 3, 10 to the minus 4, up to 2.3. In 2014, Ranheli, Chesens, Christian, and Neumeier showed that essentially if about 10 to the minus 4 below the Hopf bifurcation, that there's no slowly oscillating periodic solutions. And if there are any slowly oscillating periodic solutions in the remainder, they have to have a small amplitude. And so in the work that follows, together with Lessard and Mischaikow, we used a rigorous numerical integrator to essentially extend the proof that she did all the way down to 1.9 to show that there's a unique slowly oscillating periodic solution. And this sort of argument is based on a topological index theorem and rigorously showing that the periodic solutions are asymptotically stable. Then together with Jan Bouwe Vandenberg, we did a Hopf bifurcation theorem that really looked at all the particular estimates and showed that the branch goes up a certain amount and connects with the work of Jean-Philippe Lessard, and also backwards, that using this Hopf bifurcation analysis, we were able to rule out the existence of slowly oscillating periodic solutions for alpha parameters less than pi/2. And then in the final bit, which is going to be the primary topic of today's talk, I did a global optimization sort of approach to ruling out the rest of the possibility of there being any other isolas or islands of periodic solutions. All right, and so together through the work of many mathematicians, we have been able to prove Wright's conjecture and Jones' conjecture. And so I really like this last case because I think it's a very fickle case, which I think is difficult, but the proof works. So I think it's very nice. So there are several obstacles. The first obstacle is that this is very far from the asymptotic regime. She's argument that there's a unique periodic solution is predicated on showing that if all the periodic solutions are stable, then there has to be a unique slowly oscillating periodic solution. But the fact, and also dealing with paper and pencil estimates for if you have a really strong nonlinearity, then you can really write down what the periodic solution looks like. But in this intermediate region, you just went past a Hopf bifurcation, and so the dynamics are close to center. It's not super attracting, but it's also not close enough to the Hopf bifurcation. So 1.9, it's compared to 1.57. It's not really going to be reasonable. I mean, the amplitude of the periodic solutions over here is about 2 or so. So it's not super reasonable to make a small amplitude assumption. So you're not going to be able to extend a Hopf bifurcation analysis there. What else? And so it's also not just showing that there's a branch and you're doing a local analysis on the branch. What you really want to do is to rule out things that are far away from the branch. And so that takes a really global approach. Now, to do this, what we do is first we need to obtain a priori bounds on all SOPs that could exist if we want to rule out SOPs. then what we do is we interpret Wright's equation as an f of x equals 0 problem in Fourier space. We want to locally prove when solutions exist. And we want to be able to rule out solutions when they don't exist. So two things. All right, so to talk a bit about the Hopf bifurcation part of it. So together with Jan Bauer, we constructed an explicitly defined neighborhood where the only slowly oscillating periodic solutions could be on the principal branch. And so in particular, that means we were able to show that there were no SOPs beneath pi over 2 into the region connecting up with Verheugens, Sessions, Christian, and Neumeier. But also, we were able to show that there's no folds up to a certain point, and also up to a certain point, if you had any small solutions in the L2 norm of the derivative, and the frequency was close to the Hopf bifurcation, then the only thing that could exist was the solutions on the principal branch. And so this third point is really what we're going to use in getting rid of this middle region. So that it's essentially, if we're close to the Hopf bifurcation and we have a small solution, then the only thing that can exist is the things on the principal branch. And so for the a priori bounds, in the 1962 paper by Jones, he gets some rough estimates. He's able to show that, I mean, it's fairly easy to show that the -1 is a minimum for Wright's equation, because -1 is an unstable equilibrium. But also getting an upper bound, and then also getting upper bounds on the amount of time it's positive, and then upper and lower bounds on the amount of time it's positive, and on when it's negative. And so just from these bounds that Jones constructed, we can sort of write a very rough enclosure here, that we know it's going to be bounded above by this line, we know it's going to be bounded below over there, and it's going to be positive for a certain amount of time and negative for a certain amount of time, and then it repeats because it's a periodic orbit. And so using a very simple rigorous integration technique of essentially like Riemann upper and lower sums, we're able to just sort of integrate this initial data, because this is, I mean, this is a delay equation. It depends on the current point and the previous point. And so you can use this to integrate forward. And we developed an iterative bounding scheme so that you do many passes. And at every pass, you sort of refine your initial history. And then it sort of bottoms out and it can't improve itself much anymore. And then we sort of make a cut and sort of divide it into two pieces, and then continue with our integration scheme. And when you make a cut and you divide it into multiplications, then we get multiple situations where we think a periodic orbit could exist. And so after we get all these pointwise bounds, then what we do is we convert this into Fourier coefficients. And so for this, you can consider a Fourier series. It solves one of the things of Wright's equation is that necessarily that we know a priori that the zero Fourier coefficient is 0. And we have an inner product to really zero out, or I don't know, pick out the Fourier coefficients. And so just by integration, we're able to figure out from the pointwise bounds go into the Fourier bounds, just with integration. But we can do a bit better. See, now if we have if we have a function with a Fourier series given as such, then if we take a derivative, essentially just the I omega ks, that just falls down. And so we're able to get a bound on the Fourier series using the derivative. And this bound is going to be essentially whatever this thing is, we divide it by I omega ks, the k to the s, that gets smaller when it's in the denominator as k goes to infinity. And so by taking several derivatives, we're able to get a very nice decay on our a priori bounds for the Fourier coefficients. And we're also and so we can do the first finitely many modes here explicitly. And then for the infinite number of modes that we didn't do, we get this coarse bound here, just some sort of constant divided by k to the s. And here s is 3. And so we can do this for every single derivative. Here, the tightest bound is in the tightest bound for the first mode is given by the function itself. The tightest bound for the second mode, well, it's given by either the first derivative or the second derivative. And then for the tightest bound for the third mode is given by the third derivative. And so we can take the tightest bounds of all the derivatives, take an intersection, and that gives us our a priori bounds for the Fourier coefficients. And so we define a cube in Fourier space as this intersection of all the sines and the cosine coefficients. And then we also want to include this tail part here, right? So then what we're able to do is we take all these Fourier bounds, and then this produces a large number of cubes in Fourier space. Well, we take all our pointwise bounds, we turn it into Fourier coefficients, we get cubes in Fourier space, and then we sort of chop it up a little bit. And so for here's alpha is pi over 2 to 1.6 to 1.6 to 1.7, 1.7 to 1.8, and 1.8 to 1.9. You can see that as the parameter and also the amplitude of the periodic solution increases, the tail bounds get worse. That's given in the heat map here. And you can sort of see that this looks kind of like, I don't know, a square root function. I don't know. But essentially, we have a lot of data, but we've really reduced it a lot. Okay, so now that we've done all of our a priori bound work, now it's time to rule out solutions. And to do that, we convert Wright's equation into a zero finding problem in Fourier space. And so here we have Wright's equation. We can plug in the derivative. You can plug in the function itself. And the delay here, the delay has a very nice property with Fourier coefficients. When you delay Fourier series, essentially you're just rotating the phase of the coefficients by minus I omega k, because our delay is 1. So we plug it in, we rearrange it a bit, we get our equation in Fourier space, and we know that I is going to be a periodic solution if and only if f of x equals 0. The way that the bounds came out really lends itself to using this supremum norm. We also use an L1 norm because that's sort of the language that the Hopf bifurcation came out with. But in order to divide up space here, we want to be using L infinity norms, which we're using a capital omega because just to emphasize that we're using different algebraic weights. But that's the space we use in. We have a discrete convolution. This is a Banach algebra. We know that since we want real solutions, we have parity with the negative coefficients. And so we can sort of, I don't know, clean up our notation a bit. I like to use K for my compact operators, which has some and U for my unitary operators. And so we can write out our zero finding problem as the inverse of this compact operator. So it's just a densely defined operator, plus these unitary operators and this discrete convolution. And we can compute derivatives. They're going to be Crotchet differentiable, assuming that the K inverse is the inverse of a compact operator is well defined, just restricting the domains and the ranges. Right. And so now that we have our f of x equals 0 problem, now we want to find all of the solutions, not just one, but all of them. And so for a toy problem, I like to consider this. So how do we count all of the solutions to the problem 0 equals cosine x plus 10x over 10? So, I mean, the first thing that I would do, not any numerics involved yet, just if the cosine is bounded between -1 and 1, and so I'm going to need x over 10 to be between -1 and 1. So x has to be between -10 and +10. That's my a priori bound. So somehow I get my a priori bounds. Then after I get my a priori bounds, the next thing that I want is I want to sort of go through my space and find solutions. I want to be able to subdivide my compact domain. If I'm between -10 and -9, I want to be able to rule out that part. But if I'm over here, maybe between -5 and -6, I want to be able to show that there's a unique solution over here. And so those are the two things that I want to be able to do. But I mean, I then want to extend this to not just one-dimensional domain, but I want to do this in infinite dimensional domain. And we all know that there's a curse of dimensionality, that as the dimension of your problem gets higher, things usually get exponentially worse. And so why shouldn't infinite dimensional problems be infinitely worse? Well, so for here, what we really need to exploit is the word compact, because things in infinite dimensions, they can be compact, and compact means that if you fix an epsilon, you can cover your space by epsilon balls. And so to get an intuition for what we're dealing with here, let's compare our two sort of paradigms of compact sets. One is just a normal cube, and then the other is a Hilbert cube, which is the quintessential compact set in an infinite dimensional sequence space. So here's a d-dimensional cube, and here's an s-weighted Hilbert cube. And so compactness means that if you have a subdivision number, so the number of balls with radius 1 over n that you need to cover your set. So if our subdivision number is finite for all n, then it's compact. And if we calculate our subdivision numbers, well, if we want to subdivide a unit cube into subcubes of radius 1 over n, well, we need n to the d cubes. For a Hilbert cube, you can do a little calculus exercise, and it comes out to that as a good approximation. E to the s times root s of n minus 1. But I mean, whatever. It's a formula we can plug it in, and so we can graph how do these things compare. And so you can see here in the solid line we have the subdivision number for our Hilbert cube. In the dashed line we have the subdivision number for our normal cube, right? And so you can see that initially, if we have a very coarse grain, if n is low, we want a very coarse approximation, then the Hilbert cube is a better. We need less subdivisions. And why is that? Well, the Hilbert cube's already subdivided in the tail. It's already very, very, well, it's not subdivided, but it's just like very squished, right? We have a 1 over m to the s, and so it's already tiny. We don't need to subdivide the tail. But then as our granularity increases and we're looking at finer scales, our Hilbert cube remembers that it's infinite dimensional, and then it takes a lot of times to subdivide. And sort of these intersection points you can sort of think of as over here, if you want a resolution of 10 to the minus 5, then a Hilbert cube weighted with a 5th derivative is about equivalent to subdivide as a 4-dimensional cube. And 4-dimensional cubes don't seem that scary to me. And so that's sort of the intuition for why this sort of approach could work. Now, if you're looking at the scales here, this for the granularity of 10 to the minus 5, you need like 10 to the 20 subdivisions, which is way too many. So this is not the only thing at work here. So we still need to be, we can't subdivide everything and then look at it. We need to be a bit more clever. And so essentially, when we're looking at a particular cube in Hilbert space, there are several things that we want to do with it. Because we're going to be setting up a branch and prune operation. And so there's several things that we want to be able to ask our cubes. The first thing that we want to ask our cube is, do you contain a unique solution to our f of x equals 0? Or is there a unique, for every alpha in the cube, is there a unique slowly oscillating periodic solution? Also, if there's no solutions, we want to be able to show that there's no solutions. And if we're close to a Hopf bifurcation, then we want to use a Hopf bifurcation analysis, which we already did in a previous paper. And so we just want to be able to identify if we're close to the Hopf bifurcation, put that aside and deal with that with a different set of techniques. And if we can't do any of these things, then at least we could just reduce the size of the cube. Okay, so the way that we do that is with several techniques. The first thing that we do that we can use is the Krachek method, which is expensive. We need to invert a matrix, essentially. But it's able to do several things. It's able to show there's a unique solution. It's able to show there don't exist any solutions. And it's also able to reduce size of cubes, even if we're not able to fully do other things. And a cheap thing that we can do is just evaluate the function on the cube. If we just evaluate the function using interval arithmetic and the bounds show that it's bounded away from 0, then we can just reject the cube. That's fairly cheap. If all the Fourier coefficients are small, well, 0's an equilibrium, and we can sort of prove a nice little theorem saying that if we have a small amplitude, then 0 is the only solution. There's no periodic solutions. And so if all the Fourier coefficients are small, we can reject it. And also we have an explicit method to determine whether we're close to the Hopf bifurcation. And so to talk a bit about the Krachek method, this is very similar to the interval Newton method. So with interval Newton, you are creating an outer approximation for the Newton operator. And Krachek is essentially the same, except we're expanding about the center of the cube with an approximate derivative. And using an approximate derivative here is quite important because the cube, I mean, in finite dimensions, you can invert an interval matrix, but in infinite dimensions, inverting a large class of infinite dimensional linear operators is difficult. And so we just need an approximate inverse. We don't need to worry about exactly inverting things. But all that aside, with the Krachek method, we're able to show that the Newton map is contained inside the image of the Krachek operator, that if the Krachek operator maps into its interior, then there's a unique 0. And if and the Krachek map is going to contain all solutions that were inside the cube. And in particular, if and so essentially what you could sort of imagine this is that here we know, here's in blue, this is our initial cube. We map it forward with the Krachek map, and we know that any solutions that exist have to be in their intersection. And so using this method, we're able to reduce the size of the cubes. If the Krachek map is totally disjoint, then we can just reject it entirely. If it maps into the interior, then we have a unique solution. And so with all that in hand, right, so it's usually applied to infinite dimensions. Galias and Zhelezhinsky generalized it to Hilbert space, and there's a lot of technical distance. But the way that the whole branch and prune algorithm works is that we start off with our a priori bounds, and then we convert our pointwise estimates into our Fourier cubes. And then once we have our list of Fourier cubes, or a Q, we take the first thing off the Q, and then we inspect it with our pruning operator. And so with our pruning operator, first we see, well, is it too small? Can we just reject it easily? If yes, then we just throw it away. No need to store it or anything. If there's a unique solution, well, there's two ways that we can prove that. One is with the Krachek method by mapping into the interior. The other is with the Hopf bifurcation. Just does the result from the previous paper apply? And if so, then we take it out and we put it into our two answer piles, answer A and bifurcation pile B. If it's too small, so not the amplitude of the solution, but really is the diameter of the cube too small, because we don't want to be subdividing things ad infinitum. So we sort of set at the very beginning, we set a stopper so that if the cubes become too small, then we just say, I don't want this program to run infinitely long. I'm putting it into this reject pile R. And so if pruning was effective, so if we're able to reduce the size of the cube a lot, then it will be useful to do that again. And then we repeat that step. But otherwise, then we subdivide the cube. And subdividing the cube always reduces its size. And so we then add both cubes to the list, and then we go again. And so in summary, this branch and prune method, cubes are able to exit this loop in one of three ways. One, if the Krachek method maps into the interior, so we have a unique solution. Two, if we're close to the Hopf bifurcation neighborhood. And three, if they got rejected because the cubes got too small. And so the cubes getting too small, it really sort of ties into this sort of grid alignment problem, which is fairly frustrating. Essentially, what can happen is that you have this branch of solutions, and if you're subdividing things and you sort of haphazardly cut your solution branch in half, then you're never going to be able to sort of piece it back together and verify it. And so then you have this cascade of failures, and eventually you sort of stop. But the fix is fairly easy. These cubes that were too small, we just sort of recombine them along their alpha values, and then we check it that they get verified, and everything gets verified, which is wonderful. And so in total, we're able to adaptively prune and subdivide cubes until everything's added to the output. And there's three ways that we can add things to the output. And we're able to show that if there were any solutions, then they need to be inside the output, because we only reject things where there's no solutions. And for every cube in our answer pile and every alpha parameter in each cube, there's a unique solution to our f of x equals 0 problem. And so there's a unique slowly oscillating periodic solution at that alpha value. And we also know that any solutions in the blue bifurcation pile, any solutions need to be on the principal branch. And so in total, we're able to show that for every alpha greater than pi over 2 and less than or equal to 1.9, there's a unique swaps to Wright's equation. Right, and so just how am I doing on time?
Good. I mean, you got 10, 15 minutes.
Oh, okay. So to bore everybody with computational runtimes, so I mean, here, this is the number of cubes that were produced just by the pointwise estimates. And then when we turned it into a grid of Fourier cubes, so we were starting off with 1 to 200 Fourier cubes just to begin with. But really the two important things here is the runtime for the a priori bounds here in red, and then for the branch and prune algorithm. And so this is in minutes. So it took about 10 hours, I guess, to do the bounding functions, to do the integration and the pointwise bounds when we were close to the bifurcation. But then as we get farther away from the bifurcation, then integrating becomes easier. We're not slowed down by the center analysis where everything is very slowly converging to a small amplitude periodic solution. And when we're farther away, we have greater attraction, and then the integration method is better. But then sort of conversely, when we're close to the bifurcation and the amplitude of solutions are very small, then Fourier is very quick, and we're able to validate this in less than an hour. And then I guess, I don't know how many hours that is, but 1,300 minutes is how long it takes for the large amplitude periodic solutions. And that is also driven by, we have worse bounds on the tail. Right. And so there's some future questions that come out of this. Firstly, so there's not only slowly oscillating periodic solutions, there are the stable ones, but there's also unstable rapidly oscillating periodic solutions. And so at every 2 pi n after pi over 2, so 5 pi over 2, 9 pi over 2, etc., there's going to be a rapidly oscillating solution born out of a Hopf bifurcation. And there's a well-known theorem that every rapidly oscillating solution is a rescaling of a slowly oscillating periodic solution. And since we proved that there's no isolas, everything, all the slowly oscillating periodic solutions, they can be traced back to the Hopf bifurcation over here. That means that there's going to be no isolas of the rapidly oscillating periodic solutions. But it's an open conjecture whether there's any folds in the rapidly oscillating periodic solutions. And so there's that conjecture. A related conjecture is whether the global attractor to Wright's equation is given by the closure of the unstable manifold at the origin. This is referred to as the generalized Wright's conjecture. There's also conjecture by Konstantin that whether essentially the dynamics given by his Conley analysis gives a complete description of the dynamics, whether the semi-conjugacy that he proves is really a true conjugacy. But then there's also another conjecture, which is that the period length of the slowly oscillating periodic solutions increases monotonically with alpha. And why this last conjecture here is I think particularly interesting is because this period length of the slowly oscillating periodic solutions determines the rescaling. And it determines the rescaling in such a manner such that it implies both of these other conjectures. And so if you're able to show that the period length of the slowly oscillating periodic solutions increases monotonically with alpha, then you're able to prove these two conjectures. Currently, this is known up to like 10 to the minus 3 above the Hopf bifurcation. So maybe like 1.58, maybe. And then there's like all the rest to infinity. That's open. So that's an open conjecture. Some more questions that I think are interesting. So unlike Wright's equation, the Force-Duffing equation has isolas and islands. And so one interesting question I think would be, can this technique be applied to something where there are isolas? Maybe, maybe not, I don't know. I think it's interesting. And then also, can this technique be applied to rigorously count the number of equilibria in a PDE? So this approach was very functional analytic. And so a lot of the same sort of analysis can be done with PDEs. And so I think that's also an interesting question. All right. So thank you very much for your attention. And I'm happy to answer any questions that you might have.
Jonathan, thank you very much. Okay, very, very nice, very nice. So we have plenty of time for people's questions. So who'd like to get us started?
Well, if I may.
By all means.
So, first, a pre-question, so to say. When you talk about cubes, when you subdivide it, does cube really mean something like a cube with equal lengths, or is that just a rectangular object?
Oh, the Hilbert cube, yeah.
The Hilbert cubes. Yeah, when you're talking about cubes all the time, but I guess you can also take rectangular cuboids.
Oh, yeah. That's true. These are not.
These are not cubes in the strict sense.
Yeah, right? Correct. Yes. They so can be lopsided and very long and skinny.
And that's so that was the pre-question. So when you now subdivide such a rectangular object, then how do you decide about the direction in which you further subdivide? So that means you must identify in some sense critical direction in which you need subdivision. And how is that done?
Yeah. Let's see. Here. So, right. So the sort of computational parameters, in what we did, we stored 10 Fourier coefficients. So 1 through 10, and then the rest is tail. And we also storing in each cube the alpha parameter and the omega parameter. And so we only were subdividing along the first alpha, omega, and then the first 3 Fourier coefficients. And then coefficients 4 through 10, they just sort of stayed along for the ride. We didn't subdivide them, but sometimes they would get smaller because of the Krachek method, sort of reducing the size of cubes. And so to answer your question, how did we decide which variable to subdivide along? Well, here, I mean, we did a sort of naive method, which was we cut along the variable which had the largest diameter. We weighted it a bit to make, because there's a problem with alpha. Now, if this was not parameter dependent, then there's several heuristic methods for which direction to cut along. Essentially, if you have a lot of variation, this is not described by the derivative, then that's good to cut. Or if you have a lot of variation, that direction is good to cut. It doesn't matter so much how large it is as so much as the variation. But the real problem was that I couldn't find a good heuristic to deal with alpha as a parameter. And so we just stuck with the more naive of which is largest.
When in the previous step, you were not successful with proving this enclosure by the Krachek operator, then would that not, so that the way how it is not successful, would that not give you a hint in which direction you should subdivide? So to say, if the Krachek map of the Krachek operator escapes in certain direction from the original set, then in that direction you should subdivide. Isn't that true?
That sounds like a good idea that merits further looking into. I'm not, yeah. So the problem with the parameter, I mean, yeah, I think that's a good thing to look into, definitely. The problem with the parameter is that, I mean, you have sort of n equations and n+1 variables. And so there's this extra variable that's floating around that you want to get intuition for how to subdivide.
Okay, thank you.
But yeah, I mean, have you? Yeah.
Did we lose our chair? I think we did. So
Well,
momentarily.
I'm here, but it's a little bit loud here for a moment. So
Okay, I see.
if you'll take over for 1 second.
Yes. Well, are there any other questions or comments?
I just had a quick question of whether anything could be gained by a change of basis. Is there anything you can do to sort of tweak the basis slightly to be better suited to the problem?
I mean, possible. So I think when you're working at a local level, that then definitely working in a basis which is well adjusted to the problem you're looking at is definitely, I would recommend doing that. The problem here is that you're sort of with these, yeah, so sort of like with these sort of problems here, you're thinking like, well, this is clearly not well aligned with the problem. The sort of what stopped me from doing that is that you're really doing a global to local sort of analysis. And so if you do a change of basis at a global level, it's hard to do that without knowing beforehand how it should work at the local level. But then also you want to be able to recombine these cubes to make sure that if you're at a fixed alpha, that there's only one cube above here where there's a unique solution. And so if you do a change of basis, you'll have to do a change of basis back to make sure that everything fits nicely. But yeah, locally, I think that works well. The Krachek operator kind of a little bit does that, a little bit, in that you're expanding about the center. And so, I mean, you're doing an approximation of the function, but in terms of how the cubes are then recombined and you're intersecting them, that's not done in the adapted basis. And so that could possibly be improved.
Other questions for Jonathan?
I have a question. What do you think? Can you do the same for the next hop branch? I mean,
Yeah.
do you think that it's only a question of time to get the same type of results, or is there any technical difficulty, any new difficulty, or difference that you have a slowly oscillating branch or rapidly oscillating branch?
Yeah, so this I don't have anything, I don't have good news for you, which makes me sad. So I mean, you can do this up to a point. So I mean, the rapidly oscillating solution, you can get bounds on what the period can be. I'm not sure about the amplitude bounds, but the problem that I've had in doing this is how to deal with infinity and how to prove anything. Well, I mean, I've mostly looked at the period length. And so for just a finite parameter window, I think you could do something. Definitely. But I'm not sure how to connect it to infinity.
And there is a very similar class of equations where you have instead of a negative feedback, you have positive feedback. And then when you usually you have if you linearize, you have either a positive eigenvalue, which means that you have a one-dimensional unstable manifold, and then the question is whether, I mean, until the first Hopf bifurcation, you have periodic orbits or not. So it's something similar to Wright's conjecture. And after that, after the first Hopf bifurcation, the question is the uniqueness of the periodic orbit. Even locally, I mean, in a window, it's an interesting thing because it appears, I mean, in many other problems, and it's related to the existence of connecting orbits or homoclinic orbits. So it's also interesting. Do you think that it's the same? I mean, something should work.
I think so. I mean, the nonlinearity there, is it a polynomial? Is it an exponential? Or is it?
Oh, it can be a polynomial.
Yeah. Yeah, so
it's a nice analytic.
Yeah, I think polynomials should be nice to work with. Jean-Philippe, do you have?
Not more than what you're saying.
No, I think it would I would say it has a good probability of working. No guarantees, but I would be confident going into it that you would get results.
Okay. Thank you.
Yeah, because the Fourier approach, the Fourier approach does not care about stability. The Fourier approach does not care about stability. The a priori bounds that I got with the integrating technique, that will converge to the global attractor. So that you could get stuck there. But Fourier does not care about stability, and that will work fine.
Okay, good.
Jonathan, you mentioned the this recombination problem where sometimes when you subdivide it like infinitely fails and you have to like recombine your cubes in such a way. So I guess that's primarily because, as you said, having the parameter dependence makes things more complicated. I was wondering if you could just talk about that, why you get all those failures and why you have to do this recombination again.
Oh, right. Okay, so I mean, the goal here is to create a green box. And the way we create a green box is if the box maps into itself under Krachek. And if you do that, then there exists a unique solution for every parameter in the interior of the box, because the box mapped into the interior. Okay, So where does this go wrong? Now, over here, you can see there's two boxes here, a red on top and a red below. And we cut this here because it's doing a subdivision method. It's just subdividing things how it wants to. And so just at some point, there was a subdivision and this got cut in half. This is where the branch of solutions is. And so this box up here, it used to be larger and it just got subdivided and subdivided until it got small. But there's going to be some parameter here, which is like right on the branch in between the two boxes. And no matter how many times you subdivide, that point on the boundary is never going to be in the interior. And we need the solutions to be in the interior of the box, essentially. Or the interior of, it doesn't need to be interior of alpha because alpha is just a parameter, but it needs to be interior of the spatial components, alpha, the A1 here. And no matter how many more times you subdivide it, it's never going to be in the interior. So it's not gonna, this creates this cascade of
Okay.
failure.
Okay, and you resolve that by, sorry.
We fix this minimum size so that we don't go on ad infinitum.
Okay.
And then
okay.
and so that after the program is stopped and we have a bunch of these red cubes that were just too small.
Yeah.
We just go through one by one and saying, okay, match up your like if there's a box here, down here, and a box up here with the same alpha component, then we recombine it.
Okay. Okay, and then just restart there. Okay, thank you.
I have an additional question. You talked about the slowly oscillating and the rapidly oscillating solutions and made a clear distinction between them. So mathematical, of course, you can say that is slowly oscillating means, as you said, that there's at least one period of where it is positive. There's one period of time length 1 where it is negative. But what is the mathematical difference actually when you deal with all these computer assisted proof technique? Where does the property of being slowly oscillating enter the calculations and the computations?
Oh, well, so in some sense, so in the computer, or I guess with the a priori bounds. Okay, I'll just stick here. Okay, so here's some a priori bounds. One of the bounds that we have is on the frequency that we're looking at. One of the sort of things that you need to watch out for is if you have a solution and it has period n. Well, if you just go around a second time, then you have a solution of period 2n. And so we want to be able to rule out that sort of thing. And so here,
but that gives rise only to some upper bound on the frequency. So so this period length 1 is a bit artificial in that sense, isn't it?
Well, the period the 1 has to do with the delay. If your delay was 2,
right,
then slowly oscillating would be 2 length 2 positive, length 2 negative, and so forth.
Yeah, but your a priori bound you could also make on twice, on 2 or 3 or 4 as a period length. So what is the advantage of making this 1 as the borderline between the solutions you are looking for and those which you are not looking for, or which you neglect or don't treat? So you could also define slowly oscillating means the period length is less than 4, less than 5, or whatever. Fix any number, and is there any reason for fixing this 1? Well, okay, it's related to the period length. It's related to the delay, of course, but nevertheless, concerning a priori bounds and such questions, you could also take another bound here and then capture more solutions. A part of those which you so far called rapidly oscillating would also be captured then.
I mean, this in part, I'm going to try to answer this as best I can. I think this in part goes to what sort of dynamics you observe. This is a negative feedback system. And so when your history is negative, all negative, then you want to increase. And when your history is all positive, you want to decrease. And so the sorts of periodic solutions that one observes are when they're stable or slowly oscillating with the length 1 time 1 as sort of a minimum. I don't think if you increased it to length 2 or 3, I don't think you would observe more. I mean, it's at least time 1. So it's not, it's also subsuming things that are at least time 2 positive and then at least time 2 negative.
But then you would prove more. Then you would prove that there are also no other solutions which have a period length of 2 or 3 or whatever, then you would still also exclude them outside your main branch, and that the proof would give a stronger result, wouldn't it?
I think Michael's sort of thinking of going the other way, like cutting it in half. Like, what if you defined moderately slowly oscillating solutions, which is
Something like that.
at least a half of the delay time above and a half.
Oh,
you know,
okay,
so
going
sort
in
of
the
going
opposite
other way.
direction.
Yeah.
That's actually what I meant. Yes, thank you.
Oh, okay, I see. Yes. So with the rapidly oscillating solutions, there is like you can get very equivalent bounds here on what the period has to be. But they're coming out, they're coming out from the Hopf bifurcation, and so you can get the normal form of what they start off looking at like. I don't. But yeah, I think you would be able to do that. Yes. But I think for me, the difficulty there is that then you're trying to identify unstable objects, which this sort of integration method where you just integrate stuff and then it converges onto the stable object, that's not going to work because it's unstable. And so you'll probably need to do something a bit smarter there.
So that would then mean that rapidly oscillating solutions cannot be detected by this approach. Is that right?
Well, so they would be able to be detected with the Fourier part. Now the Fourier part has these a priori bounds that you get. And here we were able to, by combining two approaches, we were able to prove a theorem. If we removed the first part, I didn't try just starting with the paper and pencil bounds and then only doing Fourier all by itself. I did not try doing that. Maybe that would work. But once the theorem was proved, I was happy, and
So I'm not asking to improve your proof. I'm asking if you could extend it to other objects, namely rapidly oscillating solutions.
Yeah.
I understand I think.
Yeah, so I think that's open. I think that's open. Whether, I mean, how will this work for identifying unstable objects and enumerating all of them? For that, I think, I don't know. It might be, yeah. So, yeah, I agree. That's a good question.
Thank you.
Okay, great. Does anyone have any other questions for Jonathan? Well, I think you've given us about 20 minutes of questions there, Jonathan. So we thank you for that. And let's thank Jonathan again for a wonderful talk.
Thank you.
Okay, and that's another week of the CRM Camp Seminar. Thank you again, everybody, for being here and sticking around. And we'll see you all again next week.